So Joan, as we're looking at our binomial probability note-taking guide, Joan is that student who what, Brandon?
Doesn't know anything.
Doesn't know what's going on. She's that student who after Thanksgiving break comes to take the test and she's like, whoa, 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 whoa. I'm just going to have to guess on every problem. So we're going to look at what the chances of her success on this exam are, okay? And that's a binomial probability question, so that's what we're going to examine today. We've seen this kind of question before. We're going to take it apart a little more today, okay? So it says, Joan, how many questions? Obviously, this is a very small test or quiz. 5 questions only. How many choices? So A through D? So we got A through D going on. So we want to answer a few questions eventually today. What's the probability she gets 1 question correct? What's the probability she gets exactly 2 correct? What's the probability she passes her little quiz thing? And we want to create a probability distribution. Okay? If we had a distribution, we could answer all those questions right away. So the key is creating that distribution. So how are we going to do that? What was the strategy I suggested we pursue first? Because that's what we're going to start with today. Use a blank. Binomial is the way we're going to do it after we learn. Yeah, look at your next thing on there. First, we're going to try something else, because it's not as easy as you might expect unless you know binomial already, which you guys don't. We're going to use a simulation. We've done simulations. Let's simulate it. So everybody, with a partner or by yourself, I need you to simulate this. Let's use... Should we use our random digits table or your calculator? Whatever you like best, that's fine. Okay, so be prepared to do the simulation. So I'm going to pause the video here in a second. Let's set up the simulation first, though. Assign digits to outcomes. What do you guys think? What are the possible outcomes here?
Correct.
Should we just use 1 digit, 2 digits, 3 digits? Can we just use 1 digit? I think so. Let's say 1. If a 1 comes up, it's a right answer, yeah. And then how many choices were there in each one? 4, so maybe like 2 through 4 represent wrong answers. So if you're using your random digits table, you're going to have to say the digits 5 through 9 and 0 need to be skips. If you're doing it with a random number generator, you can just tell it to generate a random integer between 1 and 4 and not have to worry about that, right? So I want you guys right now to do that simulation. Then we're going to pool all our data together and see if we can get a handle on what this distribution, this probability distribution, looks like. Okay? So stopping rule, before we do that, let's define our stopping rule just so we're clear. Our stopping rule, how many digits are we going to look at a time? Each digit's 1 question, that's the event. So when does a trial end? After. So we'll look at 5 digits at a time, because that is 5 questions, which simulates 1 complete quiz, right? So that's our stopping rule, or when a trial ends. So that's going to be 1 trial. And what are we going to count? What's our response variable? We're going to count the correct answers. Just how many total, right? So you guys, I made a table for you to do your simulation. How many trials are you each going to do?
5.
Just 5 trials. 5 trials is, of course, not enough to get close to the real probability distribution, so we'll just combine all of our answers. You guys can just feed them to me in a second. Okay? So go ahead and take a couple minutes to do that. I'm going to pause the video. You should run your own simulation and see what you get. Okay, you guys are going to have to help me keep track of what our simulation is. We're trying to use this simulation to develop our discrete random variable distribution and do it that way, like from last week, right? So what is x? What are we keeping track of here?
Number of questions.
Correct answers. So we did a simulation, and these were our results. I'm going to need help keeping track of what those results mean. So what is this one going to be? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So that's 17 zeros out of how many? So I need to figure out how many trials there were total here, right? Each one of these numbers up here represents how many trials? 1. So I better figure out how many trials there are too, right? So 1, 2. You guys see how I did that? See, it really didn't matter exactly if we all did the same number of trials even. 17 out of 41 times though, cumulatively, we got a 0. So can somebody tell me what's that percentage? Point.
0.40146.
401?
41.
41? 46? So 41% of the time, Joanne, was that her name? Joanne? Joan gets a 0 on her quiz. Yup. What's this going to be? Let's see. 1, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. 21 out of 41 times, which is what percentage? 51.21, thank you. 51% of the time, she gets 1 out of 5 questions correct. Woohoo! 20%. Okay. 3, 7, is it 13? Thanks, Richard. 13 out of 41 times. Oh man, I must have a mistake here. Because we're already close to 100%.
That was 65. Wouldn't you have to just add all of the numbers instead of all?
Yeah, you just counted all.
Oh, I should have added all of the numbers.
It's
So
65.
I don't have to skip the. Okay. You guys are looking a little funny. I should have trusted you. We still need those, right?
Yeah,
What's this one going to be over here?
it's 12.
I got 11.
Wait, yeah, it's better.
5, 6, 7, 8, 9, 10, 11, 12. You guys are right.
It's out of 65.
And then that's 2. So what do all those add up to? 65. Yes. Thanks, Montana. Hoping this adds up to like 100%. 17 out of 65. What's that? 2615. 21 out of 65. A little more.
80.76. Or the point 80.
What?
0.8076.
80? Be like 0.3. Help me out. Help me out. Hurry up. 3. Thank you, Lauren. 13 out of 65 is a little less than that. So 0.2.
It's just 1, 2.
Oh, exactly. Okay. 12 out of 65 then must be 0.1846. 2 out of 65 is going to be 0.0. And that's, of course, 0. No one got 5 answers correct. So those should add up to 100% if we round everything. It's not going to be quite it, but that's the idea. So that's creating the probability distribution of correct answers for Joan with a simulation. We're going to do it the real way here in a second and do it with a binomial calculation. But before we do that, let's answer A through or B through D. So what's B say, guys? It says what's the probability of X being equal to 1? Well, according to our simulation, that's approximately 32.3%. I want to put approximately here because even though this is all the different possibilities, I should be able to put equals. I came up with those numbers from a simulation, so that's why it's approximate, right? C says what's the probability that X is equal to 2? Well, that's going to be approximately 20%. D is the interesting one, which you're going to need on your assignment and which is more important moving forward. What's the probability she passes the test? Help me phrase that in terms of our random variable X.
3 or more. Probability X.
Yeah, you could go like that, or you could say the probability
Greater than 2.
X is greater than 2. Those are the same thing in discrete random variable land. In z-score land, they're not the same thing, right? Because of the continuousness of the function. So this is just going to be the probability of 3, 4, and 5. If you add these up, what do you get? Like 21 something? Help me out. Is that it? So there's the probability of her actually passing the test. It's about a 21% chance. Not great chance. So let's look at this a little bit more accurately now. That was a simulation. That depends on how many trials we ran and all that business. There's actually a real answer to this question out there. Because it's not very difficult. It's just binomial. So anytime we're going to look at something that's binomial, we have to check some assumptions. This is the first time this year we're going to be checking some assumptions. Not to last, for sure. So what are the assumptions? There's this little acronym. You see it?
Fits.
Fits. If you suspect that something is binomial, it had better measure up to fits. Otherwise, it's not binomial. So something's binomial if, number one, F means it has a fixed number of outcomes. Our situation, did it have a fixed number of outcomes? We could either get 0 questions correct, 1 question correct, up to 5. Yeah, that's fixed. In other words, discrete. Okay? I. Guesses as to what I means? Not Indiana. Independence of events. In other words, one event happening shouldn't affect another event happening. I don't think her guessing on one question helps her on another question, assuming that, you know, she's not like gaining knowledge as she goes through the test. That might not be true, but we'll assume she flat guesses the whole thing.
It's an assumption.
T. T is big for binomial because it's key. It's where the bi in binomial comes from. T means there's 2 outcomes only. 2 outcomes. Most of the time, you're going to want to think about like a success and a failure. That's pretty clearly the case in ours. She either gets it right or wrong. 2 outcomes. That makes this. That's the key. That's the hint that gives you that it's a binomial situation. Okay. And S, also important, very important. It's key that you have the same probability of success on each outcome. For each outcome. That's true of ours because, once again, her probability of success on each outcome is how much? Each time she answers, what's the chance she got it right if it's pure guessing? 1 out of 4, 25%. So that's definitely true for us. So we can actually get this a lot better than our simulation just suggested. On I, even if you're not sure that it's independent, it doesn't even have to be independent. There's another thing you can check. You guys see I wrote it in off to the side there? Or is it not on yours? I don't know. I changed your handout a little bit. So off to the side on I, even if you're not sure, and this time we're not even 100% sure, so even if not independent, you can check something else that works good enough. Even if it's not independent, you can do what's called check the 10% condition. You'll be reading about that tomorrow. And the 10% condition says that if this is true and this is true, you're good to go. In other words, if the number of trials times the probability of each trial, for us like 25%, if that's more than 10, and the number of trials times the probability of failure for each trial, if that's more than 10, even if you're not strictly independent, it doesn't matter. You're still good to go for binomial. Okay? So, very important condition for other things too. So that's the first time you're seeing it. 10% condition. All right, let's do this business on the backhand side. How can we find it theoretically? Let's do one of the answers. So what's the probability Joan gets 2 answers correct? We estimated it. Now let's do it for real. 2 answers correct. We're going to do this the long way first. And then I'm going to show you a couple different ways to do it the short way. Okay? So, probability x equals 2. I left a fair amount of space there, right? I said, first let's list all the ways that might happen. Help me out. What are all the different ways? There's a lot of different ways she could get 2 answers correct total.
Missed the first.
She could Correct, correct, wrong, wrong, wrong. Correct, wrong, correct, wrong, wrong. Why don't you guys list them all out and see how many you can come up with. And then once you've got that, the next part you guys see says compute the probability of each one. So this is what you want to do. Pause the video and I'll get this up for a second. So also find the probability of getting CCWWW. So let me do that with you and then you guys can go and do it yourself. What's the probability of getting the first answer correct? We decided a second ago. She's got a quarter, so 0.25. Probability of getting the next question correct. Well, they're independent. It's still a quarter. I'm multiplying because it's the probability of getting the first one correct and the second one correct and the next one wrong, which is 75, and the next one wrong and the next one wrong. So that's going to end up being 0.0264% chance. But there's more than one way for that to happen. So that's what you guys are doing. This is the long, long way. We're not going to do it this way in our assignment. So go ahead and try that, though. Important to try this little example. I'll be right back. All right, so I'm going to interject if you haven't figured it out. There's all the different 10 combinations of what could happen. So if you guys are like, well, each probability is going to be different, aren't they all going to be the same? Each time, each one of those, regardless of what order they come in, you get 0.25 squared and 0.75 cubed, which every time is going to be 2.64%. So how do you really answer this question? Let me write down the binomial probability theorem for you. And we'll see where it came up. This is it right here, though. So in general, what is binomial probability? Now I'm going to do it step by step for you. Let's go down a little bit. So what's that add up to, by the way? So for us, the answer is going to be 10 times 0.0264. What's that going to be? 20.64%. Did we do a good job simulating or a bad job? You guys have to tell me. I don't have it in my notes. What did we get for the probability of x equals 2? 20%. 20%? That's really good. I wasn't thinking we'd do that well. So we did actually a pretty good job with just, what was that, 65 trials we ran? So nice. It was pretty close. But it's so much faster to just do it with a binomial probability thing. So it says, remember that the multiplication we just wrote happens for each of the ways in which Joan gets 2 questions correct. So we need to multiply by a coefficient which counts how many combinations there are. Now I don't know, I've kind of dropped off in Algebra 2 from teaching this combination math, so like Vance might have the best shot at it. Some of you guys who've had another teacher, I've kind of stopped teaching combinations until now. So combination is a specific thing in mathematics that you have in your calculator, and it's got a little formula for it, okay? So the idea is a combination. Let me get this out of the way. How do you do a combination? In other words, choose. A combination is choosing something. So often you'll see it written like this, as n choose k. If you have n things and you're choosing k of them at a time. Does that make sense? So the way you write choose, sometimes you'll see it like this. I like this. This is how our calculator does it. In advanced math, sometimes they write it like this, as like a little matrix thing. It's kind of weird. But usually you're going to see it like this. How do you compute choose? Well, you can use your calculator to do it, or you can do a factorial formula. Oh, I messed up. -1. Yeah. Oh, I think that might be minus k. My notes might be wrong here. We'll check it. Let's use our calculator. Is it in -1? Let's double check. So this is the coefficient that's going to go in front. So then it says, so the formula for finding binomial probability in general. What's the probability that x equals anything? First, you're going to count how many different combinations there are, which for us a second ago, how many different ways of doing it were there? There were 10. So for us, we're going to get 10 when we do that combination. We'll check it out and make sure the formula is correct. I haven't used it for a while, so I forgot. Anyway, so we're going to say that is the coefficient in front, and then you're going to multiply. You guys remember we had like 0.25 squared and we had 0.75 cubed. So that part's even easier. So you're just going to go the probability of success to whatever power this is. For us it was 2, right? That's why we had probability of 1 squared and the other 1 cubed. And then you can go 1 minus p, the opposite of that probability. What exponent power is this going to have? So if this is k, these two things together have to add up to n. So it's going to be n minus k. Now that's the general way to do it. It's a kind of intimidating looking thing, but it's very easy to use, so don't let it intimidate you. Okay? So let's do it for us for a second ago. Before I do that though, I'm going to mention what the mean and standard deviation are for a binomial distribution, because that's the last thing, just to get all of our formulas down. So for a binomial distribution, anytime you're working with a binomial problem and you've checked that fits works, as long as you've got the same successive probability each time, probabilities are independent, all that good stuff, it fits. For binomial distribution, there's a shortcut. You don't have to go through any rules of variances or anything. You just got to remember this shortcut, that the mean is always going to be n times p, and the standard deviation is always going to be the square root of np times 1 minus p. And all these formulas are on the AP exam. It's not like you need to memorize them. Hopefully that's going to happen automatically. I think the AP exam is stupid to not have you memorize them, honestly. But they're there. They aren't about memorization. In the AP exam, everything is on there. You get some formula cards. And I'll give you those soon, next semester. Okay? So there's nice shortcuts to get the mean and standard deviation of a binomial variable. This guy, let's go check it out for ours a second ago. Make sure my factorial formula is right here. I'm not sure. I think that's supposed to be k. Stupid notes from high school. So, a second ago, how many problems were we choosing from? How many attempts did she get? How many different ones? How many different attempts was she guessing at? 5 questions. So we had 5 questions. And for the probability that x was 2, we're saying she got how many right? 2. So 5 choose 2. 5 choose 2 works out to what? We did it. We did it the long way. And we got 10. So it's supposed to be 10. So let's write this out with the longhand formula and then check it with our calculator. So that's going to be what? Ignore that. 5 factorial over 2 factorial, and this is the part we're not sure about. If it's minus 1, then this will be 4 factorial. It's supposed to be 10, right? Does this work out to 10? I don't know. Factorials are nice things. They do all kinds of nice simplify stuff. For instance, 5 factorial is 5 times 4 times 3 times 2 times 1. So in other words, it's 5 times 4 factorial. So this is 5 over 2 factorial. 2 factorial is 2 times 1. That's not 10. Bad high school knows, knew it was wrong. This is supposed to be n minus k. What's n minus k for 5 choose 2? 5 minus 2 is 3. So we can write this out as much as you want. There's all kinds of ways to simplify factorials. I love factorials. If this is the first time you're seeing them, you could even write it out all the way, right? That's all multiplying. Start chopping. What do we got left? 20 over... Yes. Now, can your calculator do this? Yes. I want you to do some of them longhand. If you can't do them longhand, you're going to have issues with understanding. So, let me show you how your calculator does this. Very easy. It's just a place to do it. So if you go to math and look around, What's the thing? What menu might we be using in this section? Probability. Oh, math. Probability. There's choose right there. If you press it, you've got to go back before and put 4 there, or no, 5, right? 5, choose 2, and you get 10. There's the fast way to do it. Let's finish our problem, even if the bell hits us here. So for us, we're going to have 5 choose 2 times the probability of x being correct was 25%. Probability of incorrect was 75%. What are the exponents going to be? We wanted 2 correct. Which one of these is correct? Which one of them is incorrect? Just got to make sure this plus this adds up to that, and you're good to go. So for us, it was 10 times that times that, which we got was 20 point what? I don't know. 26?
26.36.
I don't know. We had it a second ago. But you guys get the point. You should be good to go. So you got 3 problems due tomorrow. I think I'll give you everything you need.